So our lesson today is a little interesting because, hang on, remind me tomorrow. And then I'll keep clicking remind me tomorrow. So our lesson today is interesting because the actual concept and the actual idea is actually one of the more simplistic things that we will do. However, I do think it's my duty to get into the notation behind it all and all the function notation, as you'll see throughout here. What I tend to say is that, if you plan on going into math, science, engineering, upper levels, you're going to have to be able to read math notation. And so part of my job is to get you to understand calculus on a fundamental level, like pretty basic level. I try to do that and bring it down to that level. But also the other part of my job is to get you to learn math and notation and stuff. So you'll see what I mean when we get to the end of the lesson and what I'm talking about. So this lesson is all about what's called linear approximation. A large part of calculus is approximating things. When I said we're finding the slope at one point, we didn't actually do that. We found the slope between 2 points, but they were really close together, and we said, yeah, that's basically what the slope would be at one point. So we're always approximating when we're using calculus. And today is no different. So today we're going to be talking about tangent line approximations, okay, linear approximation. So I want to start off with the first example and basically show you what the concept is today and what we're going to be having to do. So if you have a function like the square root of x, well, what I want to do is approximate what the square root of 4.1 is without a calculator, okay? So I want to figure out without a calculator, what is the square root of 4.1 or an approximation for it. Now you might sit there and be like, well, it's probably like 2.1 or something like that, It's just above 2, but we can get a pretty close approximation, and here's what I want to do. It says, find an equation of the tangent line at a point on this function really close to 4.1. So what that means is I want to pick a number that's really close to 4.1 and works really well with square roots. And so 4. I want to have x be 4. I want to find the equation of the tangent line to this function at 4, and then I'm going to use that to approximate what the square root of 4.1 is. So here's what I mean. Well, first let's just think, okay, how do I find the equation of a tangent line? Well, I need to know the point. Well, if I know the x value is 4, and I plug it into the square root of x, square root of 4 is 2. So my point is 4, 2. Then I need to find the slope at 4. And this is where derivatives come into play. I want to find the slope of this function at x equals 4. So I need to find the derivative. Remember, this right now is x to the 1/2. So f prime is going to be 1/2 x to the negative 1/2, just using my power rule, just finding the derivative here. And now I want to plug 4 into the derivative and get the slope. So f prime of 4 is going to be, well, this is the same as 1 over 2 square root of x. If you pull x to the negative 1/2 down, becomes x to the positive 1/2. And then if I plug 4 in there, I would get 1/4. So I haven't done anything new yet. All I'm doing is finding the equation of a tangent line to this function at 4, okay? So now I'm going to do point-slope form. That equation is going to be y minus 2 equals that slope I found times x minus 4. So here's basically what I have done. I have the square root of x graph, okay? And let's pretend that this point right here, I'm not going to draw a big coordinate plane, but let's pretend that this is when x is 4. And I'm trying to approximate what the value is right here at 4.1. I'm like, I don't know what this is. I don't know what f of 4.1 is. So here's what we're doing. We're finding a tangent line that hits the graph at 4. Okay? That's what this is right here. This is the equation of that tangent line. And then what I want to do, I want to find what the value of the tangent line is at 4.1. So I want you to look. This dot here on the actual function, this is the y value of 4.1. Well, what I'm going to do is figure out the y value of the line at 4.1. And notice how close those two things are. basically we're saying, yeah, the y value of that line is pretty much the y value of that function. We're just making an approximation. So I'm going to plug 4.1 in for x right here in the tangent line and do some mental math. So 4.1 minus 4 is 0.1 or 1/10. That's 1/40th, and then add 2. So this is our approximation to what the square root of 4.1 is, 2 and 1/40th. This is not what the square root of 4.1 is, but if you look over here, this is what the y value is on the line, and look at how close the y value of the function is right there. They're basically the same exact thing. And so we were able to, without a calculator, figure out about what the square root of 4.1 is. That's the gist of today. All the other stuff I'm going to be talking about today with the notation, do your best to try to follow. I think it's very important, like I said, to read math, but this is the skill. You're finding a tangent line at a certain x value, and then you're plugging a number close to that x value into the line and getting an approximation. That's the gist right there. Now, let's talk about some notation here. So I have this function, okay, and this should look pretty familiar because we used this graph when we calculated derivatives, when we did the whole limit of a derivative thing. So if we want to calculate the change in y, or in other words, delta y, given a change in x, so delta x, okay, I want to find what the change in y is from this y value right here, I want to figure out how much did y change from this point to this point. Well, if you want to find change in y, just subtract your two y coordinates. So I'm going to do f of c plus delta x, because that's the second y value, and take away the first y value, f of c. Well, if you think up above, the thing we're after is the y value right here. Like, that's what we're actually after, is what that y value is right there. That's kind of what, like, the square root of 4.1 was right here. That's the thing we're trying to find or approximate, okay? So that's the f of c plus delta x. I'm after this thing. So that value that we're after, if I just add f of c over, it's whatever f of c is, which we know, plus delta y, the change in y. So I know what f of c is going to be. That's going to be the easy value to find. If only I knew what this thing was right here, if I knew what delta y was, then I'd be able to answer the question very, very easily, right? So like using this notation and kind of correlating it with this whole example up here. So what this means is this. Let's assume our x value is 4, going back to this last example, okay? So the x value is 4, or c is 4. Well, from that value, we're trying to approximate 4.1. That means the change in x is 4.1, or 0.1, sorry. And so if I want to figure out what f of 4.1 is, well, I take whatever f of 4 is, which I found really easily on the last example, right? It was 2. I take whatever that is, and I just figure out, well, what's delta y? And again, if I just knew what delta y was, I can answer the question very easily. So this is where differentials come in on the next page. Okay, I know there's a lot going on here. So it says, look at this graph. So I kind of have the same graph as the other page, but now I drew a tangent line at C. I drew a tangent line, okay? And I want you to notice that delta y, right here, delta y, is the change in y of the actual function. Like, we have two things going on. We have an actual function, and we have a tangent line in the same picture. Delta y is how much the y changed of the actual function. dy is the change in y of the tangent line. So delta y is what you guys are most familiar with, delta y over delta x. That's your change in your actual function. dy and dx are known as differentials. So it's kind of a vocab word here. dx and dy are called differentials. So dx and dy are how much the x values and y values change on the actual tangent line, not the actual function. So notice here, when delta x is very small, okay, so I have some change in x right here. And when delta x is very, very small, imagine I take like this c plus delta x and move it really, really close to c. Like let's just pretend like right here. Notice that right here, delta y and dy are pretty much the same value. This is what I was trying to talk about over here. Like the y value of the function is so close to the y value of the line. Like they're almost the same value. So when delta x is really small, delta y and dy are almost the same value. Okay? What we say is this. I want you to look at dx and delta x. Look at how those things vary. Delta x and dx are the same exact value. We're going over some x amount from c, and whether we go over that x amount on the function or the line, they're the same exact things. Dx is equal to delta x. They mean the same exact thing. Dy and delta y are almost the same value. So we say dy is approximately delta y. Like they're almost the same. Okay? They're almost the same. So here's where the notation comes into play. And if your head is spinning, that's okay. Just kind of bear with me through the last couple of lines here. All right? dy dx is another notation for a derivative. We've come across this a good amount. This is the same thing as f prime of x. Okay? dy dx is the same thing as f prime of x. The reason this notation came to be is because it looks like a fraction, and it actually behaves like a fraction. This is not technically a fraction. It's a noun. Like this is standing for derivative, but this behaves like a fraction. So much so that if I want to figure out what dy is, like if I wanted to solve this for dy, I could just multiply both sides by dx. So dy is the same as f prime of x dx. Okay. Keep in mind what we were after from the previous page. I said if only we could figure out what delta y was, then we can answer this question. Well, that's kind of where we're at this point in time. If you think back to the previous page, we said f of c plus delta x is equal to f of c plus delta y. Well, we needed to figure out what delta y was. But now look, delta y is basically dy, and dy is f prime of x dx. So we're going to replace delta y with this thing instead. Now this is kind of a formula. And when I first started teaching this class, and I kind of learned this lesson and worked through the problems and trying to figure this stuff out on my own, I thought this was a formula that I was going to have to use. And I started using this formula on like the homework problems and stuff like that. Well, come to find out, all this is point slope form of a line. And I kind of want to make that association here. I want you guys to see this. You know how I used point slope form back on the previous example? I want you to see how all this stuff that I just got to, this is just point slope form of a line. This is not a formula you're actually going to have to know or memorize or ever use, okay? But I want you to see something. So if I had y minus y1 equals m times x minus x1, I want you to look at the relationship between these two things right here. This is just the y value that I'm after. Like this is the y value I'm trying to find. So if I solve this equation for y, look at what happens. I get y equals whatever the y coordinate was, like I'm adding y1 over, that's what f of c is, plus whatever the slope is, which is f prime of c, times the change in x, and that's what dx is right here. Should have used m instead of f prime of c. I just screwed that up. Hopefully you see what I'm trying to get at. I didn't mean to put that notation. I meant to put this notation. So y1 is basically f of c. Slope is f prime of c. And the change in x is just dx. Again, still, if you're sitting there and you're like, what are you talking about, Mr. Giordano? You're still in good shape because here's what the actual lesson is. We're going to do another one, okay? Given this function, approximate the square root of 16.2. So what we do, we find a tangent line really close to 16.2 on this function, and then we plug 16.2 into that tangent line, and we get the answer. I mean, that's the gist of it, okay? So this is not a formula that you are going to have to ever be using or memorize, okay? We are going to be using point-slope form instead. So first thing I want to find, I want to pick a value really close to 16.2, so 16. So I'm going to have my c value be 16. So I want to find the point at 16, and I want to find the slope at 16. Well, if I plug 16 into the function, I get 4. So my point is 16 comma 4. And then I want to find the slope. Well, on the previous page, we already found the derivative of this. It's 1 over 2 squared of x. That's what we found on the first example. And so if I plug 16 in for that derivative, I get the slope to be 1/8. Now I'm doing point-slope form. Here's my point. Here's my slope. So y minus 4 equals the slope times x minus 16. Now I'm using the tangent line. I'm finding the y value on the tangent line because I'm going to say that's basically what the y value of the actual function would be. And you'll see how close the approximation is here in a second. So I'm going to plug 16.2 in for x. So 16.2 minus 16 is 0.2, or 1/5. So that's 1/40th plus 4. So 4 and 1/40th. So my claim is that the square root of 16.2 is basically what 4 and 1/40th would be. So I took my calculator, okay? 4 and 1/40th is 4.025. And then I took out my calculator and I was like, what is the square root of 16.2 actually? And the square root of 16.2 is actually 4.02492. It's some irrational number. But look at how close we are. This is the actual value of the square root of 16.2. This is our tangent line approximation, a linear approximation right here. I mean, we're off by, what is that, 1,000th? Yeah, 10,000th, something like that. Very, very close. So I wanted to add an AP problem that you guys might have to you will come across and actually have to apply this to, okay? A lot of times they won't just give a function. So it says g is a differentiable function. We know g of 3 is 2. We know g prime of 3 is negative 3/4. It says the graph of g is concave down on the interval 2 to 4. Which of the following is true about the approximation for g of 2.6? Found using the line tangent to the graph of g at x equals 3. So there's a lot going on here, but as soon as you guys see like linear approximation or tangent line approximation, well, we're finding a tangent line, and then we're plugging our value in. So they already give us the point, 3, 2, and they give us the slope, negative 3/4. So I'm going to write my tangent line as y minus 2. Come on. Equals that slope times x minus 3. And I'm after an approximation for 2.6. So I take my tangent line and I plug 2.6 into it. Now you should look over here. It's going to be 1.7 or 2.3. So let's see what we get. Y minus 2 equals negative 3/4. Well, 2.6 minus 3 is negative 0.4. So negative 2/5. That's going to be positive 6/20, which is 3/10, so 0.3. This is 0.3. Add 2 and we get 2.3. That's the approximation. So now I know the answer is either C or D. Okay. The next thing that they love to ask is 2.3 an overestimate or an underestimate of the actual function value? The thing you need to keep in mind is 2.3 is not what g of 2.6 is. It is not. It's an approximation. So the question is 2.3 above the actual value or below the actual value? Like if you look back at this problem, our approximation was an overestimate of the actual value. It was above the actual value. Well, the reason they tell us here that g is concave down, I want you to think about this. If you have a concave down function like this, and you draw any tangent line in the world to any point on there, so there, whatever, every value on the tangent line will be above every value on the actual function. And so if I found a value on the tangent line, that has to be above the value of the curve. So if a function is concave down, a tangent line will be an overestimate. A tangent line approximation will overestimate. If you have a concave up function, like this, then every tangent line is below. So that would be an underestimation. So since it's concave down, I know our tangent line is above the curve, so an overestimation. So C. Good stuff. All right. Let me know if you have any questions. You're the best.